Hey guys, this is Professor Janacek, and I want to go over a couple more examples where we use multiple integration over general regions. Let's take a look at our first example. We'll be finding the volume of a solid that is above the region described by xy, where x goes from 0 to 1 and y goes from 0 to 1 minus x squared, and between the curves z equal to 1 and z equal to 2 minus y. So first off, I notice that my y values are defined on x values, which means I want to integrate with respect to y first and then with respect to x. So when we write this volume as iterated integrals, two integrals, notice I am going to be integrating over this region R of my function, which will be the area between the curves. So that's going to be z minus y minus 1. Again, 2 minus y is the largest value, and z equal to 1 is the smaller of the two values. So it's 2 minus y and then minus 1. That would be the area between those two curves. Oh goodness, there we go. And then I'm going to integrate with respect to area here. Well, in this case, my area, of course, is defined on the x's and y's. And as I was saying earlier, my y values are defined on x's. So that's what I'm going to integrate first. My y goes from 0 to 1 minus x squared. The x values go from 0 to 1. And then I will integrate the 2 minus y minus 1 dy dx. Again, I'm integrating with respect to y first. So what does this look like? Well, simplifying the integrand, we have 1 minus y dy dx. Now if we'll go ahead and integrate with respect to y, that's not so bad. We still have the integral from 0 to 1 for x. Integrating with respect to y, we get y minus 1/2 y squared, which will evaluate from 0 to 1 minus x squared. And then we'll integrate again with respect to x. Simplifying this, evaluating from 0 to 1 minus x squared, that gives us 1 minus x squared minus 1/2 times 1 minus x squared quantity squared minus all of that evaluated at 0. That's going to be 0 minus 1 minus 1/2. No, actually, I guess I don't need to do all of those. There we go. Minus 0 minus 1/2 times 0 squared. If we simplify all of this, take your time with it. Let's see, we should end up with, of course, that last term is all 0. Here we have 1 minus x squared minus 1/2 times, let's see, looks like that will give us negative 1/2 x to the 4th that's 1. And I think actually the x squared term becomes 0, and then we have plus 1/2 in no particular order. You could have written that in the other order. And now this is what we're going to integrate with respect to x. So that is, what is that? Negative 1/10 x to the 5th plus 1/2 x. We'll evaluate all of this from 0 to 1. All right, again, evaluating at 0, super simple. Evaluating 1, also pretty darn simple. We end up with, let's see, negative 1/10 plus 1/2, common denominator. Put those together, let's see, I think we'll be able to reduce that. And that should be what, 2/5, 4/10, yeah, 2/5. And there we go. So the volume of this solid is 2/5. Now I did sketch this graph. You'll notice that along the y-axis we have a parabola, y equal to 1 minus x squared. That's this parabola along the y-axis. You could also possibly see it down on the bottom. Along the xy, in the xy plane we have that parabola. And along the z-plane, we have a couple of things going on. We have just that plane at z equal to 1. Again, that's just a plane here at z equal to 1. And then at z equal to y minus 2, that is another plane along this line. It's kind of this plane here, and so that's how it gets cut. And so you put it all together, there we go, we end up with this graph here, and the volume of that is 5/2. Let's take a look at this next example. We want to find the area of the region bounded by y equal to x squared and y equal to x plus 2. Now, it is true that you can set up a single integral for this, but let's use the double integral. So we're going to take the area of the region is the double integral over that region, but notice our integrand is 1, so it's double integral of dA. Makes things pretty simple to work. We just need to recognize what we're integrating across. So looking at this graph, you'll notice we have the y equal to x squared graph, y equal to x squared, and the y equal to x plus 2 graph. Now you'll notice that my x values go from -1 to +2, and the y values go, of course, from y equal to x squared up to y equal to x plus 2. I do need to make sure I know which one's on the bottom side, which one's on the top side, which one's the larger, which one's the smaller. So notice my x values go from 1 to 2. Those are not based on y values. So I'm going to integrate, again, y is in terms of x. I'm going to integrate with respect to x, with respect to y first. So I'm going to basically have something, oh, actually my integrand is just 1. My dA will be dy and then dx. So the y's go from x squared up to x plus 2. Again, make sure you've got them in the right order. The lower side is x squared, the upper side is x plus 2. The x values go from, oh, that's supposed to be from -1 up to +2. So again, make sure you're going from the lower to the upper. All right, well, if we integrate with respect to y first, that gives us, actually, I can write it over here. We end up with simply y evaluated from x squared up to x plus 2. We will then integrate with respect to x here in a bit. So that gives us, evaluating that, we have x plus 2 minus x squared I can clean this up just a wee bit. I'm going to go ahead and write this in descending order. Negative x squared plus x plus 2. And now we simply integrate with respect to x. Oh, love this. This makes this so much simpler. So integrating with respect to x gives us negative 1/3 x cubed plus 1/2 x squared plus 2x. We will evaluate this from -1 to 2. Let's see, if we take our time with this, again, make sure you watch all those positives and negatives. Let's see, I see there's going to be a 6 in there. Let's see, that's going to be a 2. One half. What else do we have? Actually, that'll be minus 1/2. That's negative 8/3. Minus, yeah, another minus 1/3. So negative 9/3. Minus 3. So where are we? Minus 3, that's 5 minus 1/2, which gives us, I believe, once it's all simplified, 9/2. So notice in this case we're just looking for an area, but we can set it up as a double integral where the integrand, remember that integrand is really just a 1 in there. So nice for that. Well, there you go. Enjoy.